It's a great pleasure for me to speak here at the Strings meeting. Today I'll be talking about some studies I did on an index which counts the local BPS operators of the six-dimensional 2-0 theory living on M5-branes, which is done with my collaborators. I think all of them are here over the past 1 or 2 years. So this 2-0 CFT, as mentioned by Professor Douglas, is a very unique quantum field theory, both as a quantum field theory itself and also as a big inspiration for various lower dimensional quantum field theories derivable from it. But since we don't have a concrete microscopic formulations at the moment, it will be very worthwhile to try to learn the most out of various effective descriptions we have in various limits, probably with some power of supersymmetry, which usually tells us much more than one can naively expect. So the precise setting I'm interested in is also exactly the same as the setting in the previous talk, namely consider the six-dimensional quantum field theory compactified at a circle, and at low energies compared to the Kaluza-Klein scales, we have effective descriptions given by the five-dimensional Yang-Mills, or super Yang-Mills if the compactification is supersymmetric. So the unique property of these five-dimensional Yang-Mills is that the apparently lost Kaluza-Klein degrees along these circles are secretly remembered by these theories in its non-perturbative sector by the Yang-Mills instantons as explained. So more or less conservatively or modestly, I'll try to mostly assume this theory as an effective description and instead modestly restrict the set of observables that I'm interested in to those preserving some supercharges. So these kind of small, some safe observables in a sense, can be often calculated faithfully using low energy effective descriptions, mostly due to the big cancellation between the various UV fluctuations between bosons and fermions. So the concrete object that I'll be interested in is actually one of the most basic observables in any superconformal field theories. I'll try to calculate what is called the superconformal index partition function on S5 times S1. And the approach will be trying to calculate it from various, basically two super Yang-Mill quantum field theories in 5 dimensions, obtained by naive circle reductions of this six-dimensional theory on various circle factors. If you try to reduce the theory on the temporal circle, you start from the 5-dimensional Yang-Mills theory in a sphere. If you try to instead take a Hopf fiber circle direction on the 5 sphere and reduce it there, your starting point is the suitable CP2 times S1 quantum field theory. So let me first try to explain to you what kind of six-dimensional quantity I want to calculate, and then try to explain to you the five-dimensional setups. So I'm going to radially quantize this six-dimensional CFT and put that on S5 times R. And I want to investigate the spectrum of some supersymmetric states or states which are annihilated by at least one pair of supercharges among the 32. And the two supercharges without losing generality can be chosen as follows. You choose one Poincare supercharge and the Hermitian conjugate conformal supercharge. And I'm interested in the following Witten index partition function, which counts the number of bosonic states minus the number of fermionic states, preserving them. Okay. You can introduce various chemical potentials conjugate to the various global charges to weight these states. And in the superconformal group, maximal superconformal group, without spoiling the Witten index nature of this quantity, you can introduce at most 4 of them. When you're going to calculate this quantity from 5-dimensional Yang-Mills on this manifold, CP2 times S1, the time direction is manifest. So for 6-dimensional chemical potential, just reduce it down to 5-dimensional chemical potentials. If you're going to instead calculate it from 5-dimensional Yang-Mills theory in a sphere, as I'll explain to you in the next slide, you have to carefully interpret this because the time direction is apparently not visible here. So the interpretation of the first chemical potential, which is conjugate to energy plus some internal momentum, is something like the inverse temperature in a sense. So it's circumference of the circle of S5 times S1. So it should be naturally identified with the square of the Yang-Mills coupling. The other 3 charged chemical potentials play the role of twisting the boundary conditions of the 6-dimensional fields along the circle. Okay? And upon doing the circle reduction to the phi sphere, they play the following roles. Firstly, the chemical potential for the internal charge, the part of the R symmetry, SO5, turn out to contribute to the mass of a hypermultiplet in 5 dimension, which are charged under this symmetry. The other 2 chemical potentials for the rotation on S5 will require us to study the five-dimensional Yang-Mills theory on a suitably squashed five-sphere, whose metric I'll explain to you shortly. So let me try to at least sketch you the idea on how one can engineer the five-dimensional Yang-Mills theory, which we expect to calculate the six-dimensional index. Okay? As I said, it's given by the naive dimensional reduction of the theory. And the very crucial data you need to construct a supersymmetric action here are the following. Firstly is the background, the metric. Okay? How should we squash it somehow? Squash it, I mean, that information is quite crucial. And the second information we need is a killing spinor equation, whose solutions are corresponding to the supersymmetry preserved by the field theory. Both of these data can be obtained by starting the six-dimensional abelian theory, abelian tensor theory, which is free. So you know either equation of motion or action of it, and you can do the Onist-Kaluza-Klein reduction and during this course obtain this data. So you start from the standard metric and the killing spinor equation S5 times R, incorporate the effect of twisting coming from chemical potential, circle compactify, and Kaluza-Klein reduce. You obtain these expressions, and as a bonus, you obtain all the abelian supersymmetric action on the five-sphere. Okay? So it will be strong constrained on the non-abelian action that I'll be eventually interested in by constraining all the quadratic terms. So with all these data, with some recently developed techniques, some the systematic off-shell supergraph methods, and some other clever, how should I say, some guessworks or conventional works done by, as far as I see, by Hosomichi and collaborators, to treat some off-shell hypermultiplier paths. And combining this in a little bit tedious hybrid fashion, we obtain an action which has some off-shell realization of the SU11 part of the symmetry, which we'll need to calculate the partition function. So for instance, the bosonic part of the action containing dynamical fields are given as follows. And at this moment, I might have to stress what I think is the ambiguity in this kind of five-dimensional approach, which is the following thing. So to this part of the action, which contains the five-dimensional dynamical field, in principle, there's a possibility that you can add a constant shift to the action. Okay? The shift to the action that I want is taking the form as follows. So all the terms I wrote here, possibly, is inversely proportional to the Yang-Mills coupling constant, or in the six-dimensional interpretation, positively being proportional to the temperature, or the inverse of beta. The reason I need is the following. So for this quantity on the partition function of five-sphere to be an index, counting some states, its free energy in the index version should have a characteristic divergent behavior if you take the temperature to be large or coupling constant to be small. But as I'll try to show you after calculation, if you just try to start from the path integral of these dynamical fields and try to investigate the behavior in that recoupling, without this term, all you get is 1 plus some small correction as small coupling, organized into perturbative and non-perturbative ways. So the only way of having this characteristic divergent behavior of the index free energy to have the state counting interpretation is to build this kind of terms as a constant shift, which takes this form. It can be organized. I mean, in all examples I studied, it can be organized into a form of some integration of a local term coupling to some background fields like the curvature square and other background fields. I don't know how to tune the coefficients of this desired term. So the practical proposal I'm making is to tune all the non-zero necessary coefficients to favorable values if that helps you to have an index interpretation of the quantity. It's not a really stupid fitting because you're fitting the values of a several finite number of coefficients, and the information you get is infinitely many. The power of non-BPL states, degeneracy, and so on. So it's predictive. Okay? So with these understandings, having the action, you can write down the supersymmetric path integral on the squashed sphere and try to do the path integral calculation at finite value of the coupling. I should say that the ratio of the G Yang-Mills square divided by the sphere radius to make it dimensionless. Okay, so I believe the procedure of calculating supersymmetric path integral has been explained extensively by Sungjae Lee. Unfortunately, I couldn't attend the talk. But the basic idea is that the path integral and the action appearing in the path integral can be deformed by suitable Q-exact deformation without spoiling the result. So with a favorable Q-exact deformation, you let it dominate over the original action, and a formal saddle point approximation is giving you the exact result. So extensively applying this idea, and after some tedious calculation, All you have to investigate is to classify the set of saddle points and do the Gaussian path integral around them. So saddle points are given as follows. It's easy to explain the structure of saddle points on the round phi sphere, and then try to incorporate the effect of coming from the squashings or the angular momentum chemical potentials. These are the saddle point equations, and the most important part is the first box part, and it refers to a killing vector which generates a translation on the Hopf fiber of the CP2 base, whose direction is chosen by the bilinear of the spinner that are used to define the index. Okay? So the saddle point equation says that the gauge field becomes the self-dual Yang-Mills instanton configuration on this base. And the self-dual condition is in the convention that my Kähler-2 form of CP2 is anti-self-dual. Okay. If you further incorporate the effect of squashing, the saddle points equations are deformed in a complicated way, and many of the solutions which survive this equation cease to survive the squashed equation. So there's kind of obstruction. And the only kind of solution that we find, only class of solution that we could find to survive the squashings are the followings. So they are given by the self-dual instanton configuration on the CP2 base, whose non-zero field profiles are singularly localized on one of the three fixed points on CP2 under the U1 square isometry on it. So these U1 square isometries are exactly the two angular momentum are used to define the index. So basically, it's requiring us to study the behavior of self-dual instantons on the local R4 times S1. So it's a kind of instanton loop. The solutions away from all the fixed points, solving all the other equations, are obtained as follows, which are labeled by one matrix for the expectation value of scalar in the vector multiplet. Once you know the saddle point structure, the determinant coming from the Gaussian path integration can be evaluated using some clever index theorems. Let me explain you the structure of the result that we get. So the whole path integral is boiling down to a suitable matrix integral, where the matrix comes from the saddle point for the vector multiplet scalar. And the measure of this path integral, apart from the Gaussian measure here, apart from the Gaussian integration measure, which comes from the classical action, are factorized into three. And you can understand each part of the three factorized expressions as acquiring contributions from one of the three fixed points on CP2. So you can identify each part as what has been well known from the work by Nekrasov. Namely, you can identify each part as the partition function of supersymmetric gauge theories on R4 times S1 with omega deformations. That has been calculated by Nekrasov, and this is exactly the same thing once you do the careful parameter matching. So it's really a complicated expression, but you get a really concrete form of the measure and the matrix integral. But unfortunately, it's not organized into a form that we want, because it naturally is organized into a perturbative plus instantonic corrections. So it's a kind of recoupling or high temperature expansion. But most importantly, we want to understand the structure of the degeneracies of BPS states in 6 dimensions. So really, what we really want is the Fugacity expansion or the strong coupling expansion. So whether we can do this re-expansion or not is a question. At least so far, it hasn't been done concretely keeping all 4 chemical potentials. I believe with the recent developments coming about this instanton partition function, it could be doable in the near future. But in my talk, let me just explain to you some simple cases which I understand concretely. I'll try to cleverly turn off 3 of the 4 chemical potentials. The only remaining one is just the coupling constant, or the beta, in a way that the path integral measure, or the 5D supersymmetry Yang-Mills, is enjoying some enhanced supersymmetry. In particular, if you turn it off this way, the 5C Yang-Mills theory actually turns out to enjoy maximal supersymmetry, which is 16. So due to this extra cancellation, technically lots of simplification appears because the matrix model measure, which was complicated, simplifies a lot. You can do the integral and you can do the re-expansion. The results are the following, which you find for the A and D gauge groups among the ADE. The reason for why we can do it for the exceptional gauge groups is that simply that the Nekrasov partition function is not known for exceptional ones. Okay, we have some conjectures on it, but it's not proved anyway. So anyway, for the UN and SO2 and cases, do the strong coupling expansion, indeed what you find is that the Fugacity expansion all have the integer coefficient. So it's a kind of strong indication that the apparently invisible time circle is visible in the strong coupling limit. Okay? The prefactors will play the role of shifting the energy of charges of all the states by a constant amount. So it's something like the vacuum energy, which I'll explain in the next slide. The red boxed parts are giving you the information about the excited states or operators that are counted, and you can easily see what kind of states are being counted here. The only way I can heuristically explain is by appealing to an analogy, because I don't have an independent way of calculating it from 16. But exactly an analogous sector is existing in the four-dimensional Four-Yang-Mills theory. Okay? There, these are exactly the partition function of the maximal super-Yang-Mills theory for the local operators made out of one complex scalar and one holomorphic derivative. Okay? So this is in the cohomology convention that Shi-Yin should have mentioned. It's not the actual dilatation eigenstate, but this plus some Q-exact deformation will be the true dilatation eigenstates. Okay? So it's quite natural that we get this kind of partition function. Since we know this kind of analogy, it's quite heuristic to assume that we are counting something similar in this seven-dimensional theory. And having identified this kind of thing, it's not surprising, at least to me at all, that the large n limits of these indices are completely agreeing with the supergravity index on ADS7 times S4 or S4 multiplied by Z2. Because the 11-dimensional supergravity on these manifolds indeed have these states as a graviton particles. Indeed, one finds a complete agreement. Let me try to explain you the remaining prefactor. So it's a kind of vacuum energy of a quantum field theory put on a curved manifold, S5 times R, but compared to the normal Casimir energy that one usually considers, it has a couple of differences which are related to each other. So it's easy to explain what these Casimir's energies are, at least conceptually, for the free theory. Okay? So in the free theory, Casimir energies are nothing but the collection of zero-point energies of the harmonic oscillator for the free particles. So it's a trace over these zero-point energies. The first difference is that the quantity that we are calculating, the chemical potential that we are inserting is not dual to the energy itself, but some energy plus some internal charge to make it appear in an index. Okay? The second more crucial difference is that these kinds of infinite summation have to be suitably regularized. And if it diverges, it has to be renormalized by suitable subtraction. Both procedures are severely constrained by symmetries. The symmetry that is normally required to calculate the normal Casimir energy is, of course, the rotation symmetry on the phi sphere and the internal symmetry. So the only regulator you can use is the energy itself. On the other hand, all calculation that we are doing is severely constrained by supersymmetry. And in our case, in the unrefined case, the maximal supersymmetry. And the only regulator you can introduce compatible with maximal supersymmetry is just this one. The charge itself are used in the index. So with this difference, it's quite easy to see that the two quantities are closely related conceptually, but quantitatively somewhat different observables. And you can easily illustrate this difference by calculating the two quantities from abelian theories. This is what we capture in the index. This is the Casimir energy in the normal sense. Maybe more interestingly, you can do the same exercise for the UN in the larger limit. The index version of Casimir energy we take from our result, it's this. And the proper Casimir energy that people are more interested in can be calculated in the larger limit from the ADS7 dual. Okay? Not surprisingly, they are different. But somewhat curious point is that both are exhibiting n-cube behavior, which could be a robust illustration that our index is somewhat indirectly capturing the n-cube behavior of some observables in the six-dimensional 2-0 theory. Maybe to robustly illustrate that this is one of the many n-cubes that we observe, it should be desirable to do a similar calculation in the ADS7 dual, in pretty much following the way that this quantity is calculated, but making every step supersymmetric, as we did here. Now, in the remaining time, maybe 5 minutes of time, I'll try to change the gear and try to explain the calculation of the same quantity from a slightly different 5-dimensional quantum field theory, which has its own benefit, okay, compared to the phi sphere calculations. So the idea is to take the phi sphere, the top vibration of the phi sphere, and somehow try to reduce the theory there to have a quantum field theory on CP2 times R. To make this procedure a little bit stepwise, let us first introduce some ZK orbifold, where the orbifold acts as a fractional shift on the on the angle of the whole fiber. But to make this ZKOB4 supersymmetric, you have to combine or twist this shift with some internal symmetries, okay, to have some surviving supercharges. There are many ways of doing these twistings with internal charges. So as a result, you obtain many possible quantum field theories living on CP2 times R. If you do this procedure at large K, the size of this circle becomes small. So the field theory you will be obtaining will be a low energy effective field theory when K is large. The ultimate interest of our case is, of course, K equals to 1 when there's no OB4, because that's the proper 6D theory we want to study. There, the field theory we'll be obtaining will be, of course, strongly coupled, but the hope is that incorporating the effect of instanton particles completely will let us restore at least the BPS spectrum appearing in the index. So closely following the logic that I explained to you for the case of phi-sphere, the on-shell and off-shell action of the 5-dimensional Yang-Mills theory on CP2 times R can be obtained having this part of the off-shell superalgebra, which is all we need to do the calculation. And then you can calculate the index, the partition function. The good point about this kind of approach is that since time direction is manifest, the index nature is manifest already in 5 dimension. There's no fancy thing you have to do to re-expand it as strong coupling and so on. It's just an index. Okay. The small price you have to pay is that the saddle point structure and the final expression you get is a little bit more complicated than the result you obtain for the phi-sphere, but it's no big deal. So for instance, the important difference at the saddle point condition is that contrary to the case of phi-sphere, where the self-dual instantons were just allowed, localized on the fixed points of CP2, there's a little bit of anti-self-dual components of the gauge fields allowed at the saddle point, as far as it's proportional to the Kähler-2 form. So saddle point space comes with an extra integrally quantized parameters for the quantized field strength in the anti-self-dual part. Okay? So the final expression you get is somewhat similar. You get some classical contribution, and all the determinant contributions are factorized into 3. And each of the 3 parts, again, can be identified as the Nekrasov's instanton partition function on omega deformed alpha times S1 with a little bit of different identification between parameters. Okay? And the result you get is a little bit more complicated than phi-sphere. Firstly, because you have an integral. This time the integral comes from the saddle point moduli coming from the gauge field's holonomy on the circle. Okay? So naively one expects that on the complex plane you have to do an integration of a unit circle, but there's a little bit of trickiness and you have to choose the contour very carefully in a non-trivial way. The second complication is that you have to sum over all the anti-self-dual fluxes. It's making the structure of the whole index somewhat involved, but it's a very concrete expression which is manifestly an index. Having an expression which is manifestly an index, you can easily do the low energy expansion and see whether the low energy degeneracy you get is consistent with the result you know by different methods and so on. For instance, if you scale the chemical potentials carefully, the energy expansion of this index turns out to be the instanton number expansion. So far we have done the expansion for 2 or 3 instantons and so on. For instance, up to 2 instantons, we completely shown that the larger index is agreeing completely with ADS7 times S4 supergravity index, this time keeping all 4 chemical potentials. We have done a little bit more complicated test beyond the 2 instanton levels. Namely, we find that even for finite indices, the result is completely agreeing with the gravity dual as long as the energy is not exceeding a threshold given by n, which I think is quite a usual behavior. So I think the evidence is very non-trivial that we are getting a correct result. So, okay. So I try to briefly summarize what we got. I try to explain to you that 2 kinds of 5-dimensional partition function on S5 and CP2 times S1 are indeed becoming the index of 6-dimensional index on S5 times S1, the superconformal index. I explained to you some supporting evidences for this kind of claim, and some of the claims that I couldn't explain, supporting evidence that I couldn't explain to you are just listed here. For instance, for the general abelian theory, it has been shown that the 5-sphere partition function is indeed becoming an index by a work by Lockhart and Waffa, and 10 days after by ourselves. And for the case of CP2 times S1, it has been shown by ourselves, which is to appear soon. There will be various applications of the 2 kinds of partition functions I got. For instance, the CP2 times S1 index, due to the manifest nature of the index nature of this quantity, could be useful if we generalize our program to some 6-dimensional 1-0 CFTs. The 5-sphere partition function already have been used in various different contexts if we change the matter contents. It has been used to study some 5-dimensional superconformal field theories, and recently a curious observation has been made by Nieri, Pasquetti, and Passerini about its relation to some 2-dimensional CFTs, which I think Sarah will talk about tomorrow. So yeah, this is the last moment to throw out, and I'll finish my talk here. Thank you.
So shall we take a few questions? Yeah. Should I, yeah, sure.
Can you analyze how the index behaves at large n and large energies compared to n, just to see what the growth of states is like at energies of order n cube?
Yes, in the unrefined case, it's easily analyzed to be the linear power of temperature, presumably due to big cancellation between bosons and fermions. In the most general case, we have no approach from 5-sphere yet. From CP2 times S1, it might be analyzable, but we haven't done it yet. But it's just turning on more chemical potential.
I think implicit in what you said, so the small instanton singularities in moduli space you treat the same way as Nekrasov.
Yes. It's not really clear what the I mean, the prescription should be somehow a smaller important UV input, but technically what I did was take the intermediate result on alpha times S1 and just copy essentially what Nekrasov had done. I'm not really sure what physically that might mean. Yes.
Any other question?
So can you explain what happens if you just take U1?
Take U1.
Yeah, just U1.
Yes, so in the case of U1, what happens is that the perturbative contribution is really trivial. I mean, it's just free, right? But including this small instanton effect that Professor Douglas has mentioned, it acquires non-trivial contributions. So the agreement I don't have a formula, unfortunately, I erased it, but the agreement that we found here and here, especially here, are mostly coming from this small U1 instantons contribution. That's what makes this equality possible.
How do you treat these small instantons?
The way I treat small instantons, I mean, I don't have a really physical way of saying it, but I only can give a technical answer. So as I told you, the intermediate quantity in our calculation is try to identify, is identifying this with Nekrasov partition function and on S4 times alpha times S1, that one can see. And on alpha times S1, for instance, in the UN case, Nekrasov could introduce non-commutative deformation to make it into a regular field theory soliton. It might not be that on the field, in the 5-sphere, this non-commutative deformation could have physical meaning or not, I'm not sure. But what he did on alpha times S1 is something like that, and we just borrow this result.
I see. But this really begs the question, because you needed some prescription how to put in the small instantons, the small U1 instantons, because you know that they should be there because these are the Kaluza-Kleins from 6 dimensions.
Yeah.
But given that you have to add such a thing by hand, how do you know that you don't have to add other things by hand at short distance?
Sorry, I didn't get the question. How do I know what?
Let's compare the U1 situation. You know that you have to add these instantons in order to reproduce the Kaluza-Klein modes from 6 dimensions.
Yes.
That's how you know that they should be there.
Oh, how do I know whether in the non-abelian case I did the correct thing?
Right.
I don't know. I mean,
you don't have
yeah,
to add another
in the non-abelian case where I don't know an independent answer, I have no a priori justification whether the prescription I used, copy from that crossover, is relevant or not. Maybe I just copied it without proper justification. That's the status.
Okay, any other question? Maybe we can take one more. Yeah. So if not, let's thank the speaker again.